Welcome back. So, before the break I was talking about the assumptions that underlie the calculation of YTM. They were number 1, the reinvestment rates equals the YTM of the instrument, and number 2, the instrument is to be held, or the investor's holding period of the instrument equals the maturity of the instruments. Both are encoded in the formula that defines the YTM. Firstly, as you can see on the slide, the reinvestment rate is clearly equal to the YTM on the this is evident from the right hand side equation, and in the left hand side equation the summation extends from 1 to capital T, which is the maturity of the instrument. In other words, we are discounting all the cash flows of the instrument or from the instrument up to the date of maturity of the instrument, including of course the redemption value. The impact of these two assumptions is that as far as the uncertainty or the market forces relevance in so far as calculating the YTM at a point in time is concerned, that is eliminated, except for the market price at the point in time at which the instrument at which the calculation of the YTM is performed. The fact that reinvestment rate equals the YTM is illustrated by this example. We have an instrument of a maturity of 2 years. At the end, we have in fact two bonds with both with maturity of 2 years. Bond A gives us a cash payment or a cash flow of 0 at the end of year 1 and a cash flow of 1150 at the end of year 2, and bond B gives us a cash flow of 1026.80 at the end of year 1 and cash flow of 0 at the end of year 2. Now, the price of both the bonds is 916.8, and therefore, the YTM of the two bonds of both the bonds is 12%. Now, if how to find out the reinvestment rate, what we do is let us try to construct a portfolio, say long in bond A and short in bond B. Then what happens? The cash flow at T equal to 0 is 0. Because the inflow that we receive on account of the short bond B will exactly match the outflow on account of buying the bond A. We are long in A and short in B. So, the cash flow at T equal to 0 will be 0. The cash flow at T equal to 1 will be minus 1026.80, and the cash flow at T equal to 2 will be plus 1150, because you are long in bond A. So, you will receive the cash flow at maturity, and you are short in bond B. So, you will pay the cash flow at maturity. Therefore, invoking the principle of no arbitrage, the future value of 1026.80 must be equal to 1150, and if you work out the implied rate of interest, it turns out to be 12%. In other words, the cash flow at T equal to 1 is invested precisely at the YTM to arrive at the cash flow at the end of year 2. So, this example clearly illustrates the assumption that when we calculate the YTM, we impliedly assume that all the cash flows during the life of the instrument are reinvested at a rate equal to the YTM of the instrument. Now, issues with YTM, what are we have so far discussed the anatomy of YTM, but what is the practical importance and practical limitations of YTM? Let us now come to this particular point. The YTM measure for long term maturity bonds, coupon bonds, tells us little about the potential return that an investor may realize if the bond is held to maturity. Let me repeat, the YTM measure for long term maturity coupon bonds tells us little about the potential return that an investor may realize if the bond is held to maturity. Please note, the coupon bonds word is highlighted here. So, this particular issue may not apply when we are talking about zero coupon bonds. The zero coupon for the zero coupon bonds, if they are held up to maturity, then obviously there is no reinvestment risk, because no coupons are being paid on the instrument, and therefore, there is no issue of reinvestment. However, in the case of coupon bonds, particularly for long maturity, YTM turns out to be not a very precise measure of yield. Let us see it with an example. Here is an example where we got two bonds A and B. the reinvestment rate is given as 6.66%. The coupon on bond A is 10%, the coupon on bond B is 3%. The face value of both the bonds is 100. The current market price of the bond A is 138.90 and that of bond B is 70.22. The maturity of both the bonds is 15 years. Coupon payments are annual, and the YTM of the bond, if you calculate the YTM of the bonds, it turns out to be 6% for bond A and 6.1% for bond B. So, if we were to assume that YTM is the correct measure of yield, then obviously bond B would be preferred. But as I mentioned, a very important assumption underlying the concept of YTM is that all intermediate payments are reinvested at the YTM rate. So, while calculating YTM, what would happen is the reinvestment rate of bond A coupons would be at 6%, the reinvestment rate of bond B coupons would be 6.1%, but it is given in the problem that the actual rate of reinvestment is 6.66%. Let us see the results. These are the results. The reinvestment rate is 6.66%. The reinvested coupon at the date of maturity, that is at the end of 15 years, turn out to be 243.6823 for bond A and 73.1047 for bond B. Please note, this is the total value of reinvested coupons, total value of reinvested coupons calculated at the reinvestment rate of 6.66%. Total value of reinvested coupons calculated at the reinvestment rate of 6.66%. Now, the redemption value, as I have worked it out backwards, and in order to account for the rounding off that is done while calculating or while representing YTM, the redemption value has been slightly adjusted. It seems that it would be at face value of 100, but to account for the rounding off of YTM, we take the redemption value as 100.12223 and in the second case 100.321. The total value is 343.80. Total cash flows, that is the total value of all reinvested coupons on the date of maturity, that is T equal to 15 years plus the redemption value of 100 or approximately 100. So, the total value, total cash flow at the end of 15 years is 343.80 for bond A and 173.46 for bond B. The current market price is given as 138.90 for bond A and 70.22 for bond B. And what we find is that the effective annual yield is 6.22% for bond A and 6.21% for bond B. Now, let us recall that the YTM of bond A was 6%, the YTM of bond B was 6.1%. So, if we took YTM as the correct measure of yield, then we would have selected bond B, but because the reinvestment rate, the projected or the actual reinvestment rate as the case may be, turns out to be different from the YTM, and A has a higher coupon, therefore, the coupons of A are reinvested at a higher rate of 6.66% compared to the assumption of YTM, which is 6%. If we work by the YTM, we assume that the coupons of A of 10 units per annum is invested at 6%, but in actual fact the coupons of A are reinvested at 6.66%. What happens in the case of B? B's coupon rate is less, it is 3. So, in the case of B, the impact of the difference in the reinvestment rate, because the reinvestments are less, the coupons are smaller, so the reinvestments are less. Therefore, you end up as the yield of A being higher than the yield of B. This is because the reinvestment rate in the case of A has a greater impact in the case of A compared to that in the case of B. So, the inference is that unless and until we are able to work on the premise that the reinvestment rates will equal the YTM, YTM may turn out to be giving you a distorted picture, particularly where the reinvestment income turns out to be a significant contributor to the overall yield on the instrument. So, that point needs to be kept track of, and that is very well illustrated by this particular example. The reinvestment rate has a strong say in the overall yield of the instrument, and YTM assumes that it is equal to YTM by default. There is no choice, there is no discretion, it is the default embedded in the formula. So, if the actual reinvestment rate or the reinvestment rate projected by the investor, anticipated by the investor is different, then we should use that different reinvestment rate instead of using the concept of YTM. This is a table which I have prepared, which illustrates the returns corresponding to different reinvestment rates. You find that up to 6.66% or slightly below 6.66%, this is 6.65% precisely, the return or the effective annual yield for bond B is superior to bond A, but as soon as we cross 6% or more, the situation reverses and the effective annual yield for A becomes more than effective annual yield for B. Why? Let me repeat, because A's coupons are more, and therefore, the impact of the higher reinvestment rate compared to the YTM is felt more in the case of A, and we get a higher yield if you use the actual reinvestment rate compared to that for B, where the coupon rate is very small. And in fact, if you have a 0 coupon bond, the reinvestment rate will have no impact, because there are no coupons to reinvest. So, in the case of a 0 coupon bond, YTM will turn out to be the correct measure of yield, whatever the case may be, whatever the reinvestment rate may be. Now, the second issue with YTM. The second issue with YTM is that the YTM of a portfolio is not equal to the weighted average YTM of the constituents. Now, we all know that the expected return on a portfolio is equal to the weighted average expected return of the constituents of the portfolio. It is quite straightforward. However, when we talk about the YTM, this formula does not hold. The YTM of a portfolio is not equal to the weighted average YTM of the constituents. Let us see a simple example. A portfolio is made of equal proportions by value of two securities A and B. There are two securities constituting a portfolio. The current price of A is 100 and its respective cash flows over the next 3 years is 15, 15 and 115. Clearly, the YTM of A is 15%. It is a level coupon bond with a coupon rate of 15. So, and it is quoting at par. So, the YTM of bond A is 15%. The price of B is also 100 and the cash flows are 6 and 106. So, the YTM of bond B, which has a coupon rate of 6%, which is quoting at par, redeemable at par, and therefore, the YTM of bond B is 6%. Calculate the YTM of A and B. We have already done that. We can simply do it by observation. A is 15%, B is 6%, and for the portfolio as well. The weighted average YTM would be 6 plus 15 divided by 2, that is 10.5%. Let us see what the actual YTM turns out to be. So, A has a cash outflow of 100 at t equal to 0, and it gives me 15, 15 and 115 at the end of 1, 2 and 3 years. B has an outflow of 100 at t equal to 0 and gives me 6 and 106 at the end of first year, second year, with no cash flow at the end of the third year. So, the total cash flows are at t equal to 0 minus 200 for constructing the portfolio, and the cash inflows at t equal to 1 is 21, at t equal to 2 it is 121, and at t equal to 3 it is 115. And when you work out the YTM of the stream of cash flows using Excel, you find that it is 11.29%. And please note, please recall that the weighted YTM of this portfolio was nothing but 10.5%. So, obviously, there is a significant difference. In fact, there is a massive difference between the YTM or the weighted average YTM and the actual YTM of the portfolio. So, the portfolio combination rule, the linear portfolio combination rule that applies to expected returns does not apply to YTMs. Now, just to recall coupon rates, YTM and bond price, just to recall, bond prices and YTM are inversely related. The value of a bond would be equal to its par value only if the coupon rates are equal to YTM and the bond is redeemable at par and it is a level coupon bond. The value of a bond would be more than its face value if the coupon rate is more than the current interest rate, and again I repeat, this is applicable for a level coupon bond which is redeemable at par value, and the inverse in the case of discount bonds. Now, what is the reason for this? Let us talk about a discount bond. What are we saying? We are saying that in the case of a discount bond, the YTM of the bond would be higher or the coupon rate would be lower, the YTM of the bond, provided of course the bond is a level coupon bond redeemable at par. Now, I repeat, we are saying that the YTM is the interest rate is higher, the YTM market interest rates YTM is higher and the coupon rate is lower. Now, because the bond is quoting at a discount, the return to the investor will consist of two parts. Number one, the part of amortization of the discount every year. Suppose the life of the bond is 5 years, then at the end of the 5-year period, the bond, because it is redeemable at par, therefore the value of the bond would also be par on account of no arbitrage considerations, and therefore the difference between the par value and the market value, where the par value is higher, market value is lower because the bond is quoting at a discount. This difference needs to be amortized over the life of the bond, and therefore every year there will be a certain amount of amortization, and therefore this amortization will also contribute to the return to the investor. The investor will get return on account of two parts. Number one, this amortization part, and number two, the coupon cash flow. So, what will happen is both these parts will add together, and as a result of which the overall return to the investor will be higher than the coupon rate. And in other words, the YTM to start with would be higher than the coupon rate, but then once we work out the YTM, we impliedly assume that the reinvestment of coupon payments is also at the YTM. So, because to start with YTM is higher than the coupon rate, that means the coupon payments are also being reinvested at a higher rate compared to the coupon rate, and therefore the overall YTM increases even further. In other words, the net result is that the YTM of a discount bond is more than the coupon payment, than the coupon rate. Or putting it the other way around, if a bond has a coupon rate which is lower than the YTM, it would be quoting at a discount. Now, this theorem, for a fixed rate bond that does not default and has a reinvestment rate equal to YTM, that is given to us, an investor who holds the bond till maturity will earn a rate of return equal to the YTM at purchase, regardless of whether the bond is purchased at a discount or premium. This is quite simple, quite straightforward theorem, that if the reinvestment rate is equal to the YTM, then obviously the investor will get a return equal to the YTM at the point in purchase. We have already in fact established it earlier. You can see here again, if there is an instrument in which the reinvestment is taking place at the YTM, then the total cash flows at the end of the holding period, that is at maturity, will be given by this expression. And using this expression, if we work out the effective annual yield over a holding period equal to maturity, and simplifying this expression using the formula for geometric progression, what we end up with is that RY the return, the effective return here is equal to RY is equal to Y. So, in other words, the effective annual return RY is equal to Y, provided the reinvestment of the coupons is equal to YTM. Of course, we are talking about a level coupon bond redeemable at par. So, in the case of a level coupon bond redeemable at par, if all coupon reinvestments are at the YTM, then the return earned by the investor is also equal to the YTM irrespective of the price of purchase. Clearly, this return is independent of P0, whatever be your price of purchase, whether it is below par, above par or at par, the return that you get is equal to the YTM. The next theorem, an investor who sells a bond prior to maturity will earn a rate of return equal to the YTM as long as the YTM has not changed since purchase. An investor who sells a bond prior to maturity will earn a return equal to the YTM so long as the YTM has not changed since purchase. Let us look at this. Let us take an example first. Consider a 10% annual bond with a maturity of 5 years trading at a YTM of 12%, that is at t equal to 0, that is today. The bond is held by an investor for 2 years or is proposed to be held by an investor for 2 years and then sold off at to be sold off at a YTM of 12% again. In other words, we assume that the YTM has not changed over the holding period of the investor. We want to calculate the effective annual yield. I repeat, consider a 10% annual coupon bond with a maturity of 5 years trading at a YTM of 12%. The bond is held by an investor for 2 years and sold off at a YTM of 12%. Calculate the effective annual yield. The calculations are quite simple, quite straightforward. The current price of the bond P0 is equal to 100. 100 is the coupon payment. We assume that the face value is 1000. So, since the coupon rate is 10%, 100 is the coupon payment. 100 into PVIFA 12% for 5 years plus 1000, that is the repayment of principal. We assume that it is a level coupon bond repayable at par. So, plus 1000 into PVIF 12% for 5 years and we get the value of 928. So, the price of the bond at the point of purchase is equal to 928. Price of the bond after 2 years, please note we are given that the YTM has not changed during the life of the investment of 2 years. In other words, over this 2-year period there has been no change in the YTM of the bond. So, the price at which the bond is liquidated in the market P2, P2 means at the end of 2 years is again 100. Now, we have got 3 coupon payments. So, the present value will be calculated for 3 years. So, 100 into PVIFA 12% for 3 years plus 1000 into PVIF 12% for 3 years, that comes to 952. 952. So, the proceeds of, now we calculate the proceeds of interest. We are given that the reinvestment rate is equal to YTM, which is 12%. So, what will be the reinvestment proceeds of the interest that we receive at the end of the first year, the coupon that we receive at the end of the first year, it will be reinvested for 1 year and it will yield 12%. So, it will the cash flows or the maturity value of this coupon, reinvested coupon, will be 112 and the coupon at the end of the second year will obviously not be reinvested, that will be equal to 100. So, the total value of reinvested coupons will be equal to 212. So, the total cash flows on the point of sale of the bond will be equal to 952 plus 212, that is 1164. And when we work out the effective yield, effective annual yield, we find that it turns out to be 12%, just thereby vindicating, proving the theorem, at least illustrating the theorem. And this is the explicit proof for that. Again, it is simple algebra where we use this the expressions for the PVIFAs and simplify the expression. Nothing much really to explain except for the point, except for this point. At this point, when you simplify the whole expression, what you get is the expression within the square brackets. The expression within the square brackets simplifies to C is 1 plus y to the power t minus 1 divided by y into 1 plus y to the power t multiplied by the CF and plus f divided by 1 plus y to the power t, and this whole expression within the curly brackets is nothing but the value of p 0 by the definition of YTM. It is the present value of all future coupon payments plus the present value of the redemption value calculated at the YTM. So, the entire expression within the curly brackets it must equal p 0, and so that is what we have done in the last step. We have substituted the entire curly brackets equal to p 0, and this 1 plus y to the power h remains outside the curly brackets. And by comparing the first expression on the slide with the last expression on the slide, we find that the return earned by the investor is equal to the YTM of the bond, provided, I repeat, provided the YTM has not changed during the holding period of the investor, and provided we are talking about a level coupon bond and a bond that is redeemable at par. Now, next theorem. The value of a bond would increase as it approaches maturity if it is a premium discount bond. Now, I mentioned a few minutes back that the value of a bond on its date of maturity must equal its redemption value. A bond that is to be redeemed at face value must be quoting at face value on the date of maturity to prevent any arbitrage from taking place. For example, if a bond was to be priced at a value lower than the redemption value, what you would do is you would simply buy the bond in the market and deliver it to the company and take the redemption proceeds and take a riskless profit, which is barred by arbitrage, and therefore, it must necessarily be so that the value of the bond on the date of redemption must equal its par value. So, if a bond is quoting at a premium at an earlier date or at a discount at an earlier date, then that premium or discount, as the case may be, must necessarily be amortized over the remaining life of the instrument, because I repeat, at the end of the holding, at the end of the maturity of the bond or at the end of the term to maturity, the bond must quote at its par value. Please note that this amortization may not be linear. In fact, it will not be linear, but for the simplicity of exposition, I have represented it by a straight line. In the case of a premium bond, this is the amount of premium, but this amount of premium must be amortized over the remaining life, so that the bond comes to par value on the date of maturity. Similarly, for a discount bond, the amount of discount must be amortized by the point in time it reaches its maturity, so that it may be trading at par value on the date of maturity. Right. We will continue from here in the next lecture. Thank you.